Today, I'm going to talk a little bit about flow nets and how they can be useful for geotechnical engineers. And in particular, we're going to learn a few tricks about how to draw them and then some pretty cool calculations that we can do with them. So in the last lecture, we talked a little bit about continuity and derived the Laplace equation. And we showed how the Laplace equation could be pretty useful because we can solve for different piezometric heads or total heads at any x or y or x or z coordinate combination on a cross-section of a soil profile. And we showed how the Laplace equation could be solved for a known or a constant head, and then if we were to contour these different points of equivalent head, we would call then that contour line an equipotential line. And then we talked a little bit about how we could solve another equation similar to the Laplace equation, but perpendicular in essence to the equipotential lines, and we call those flow lines, and they represent the path that a drop of water would take to travel through the soil. And we talked about how then we could solve these different equipotential lines and flow lines using numerical methods such as finite element, or we can approximate a solution using finite difference with known boundary conditions. And I also mentioned that with a few simple rules and tricks, we could just draw our solutions by hand, almost like an artist would or something like that. And so that's what we're going to learn a little bit about today. Now, this collection of equipotential lines and flow lines on any given cross-section of a seepage problem is what we call a flow net. Now, right off the bat, let's just talk about the rules for drawing flow nets. So these rules apply if you want to draw a flow net by hand. Number one, the flow lines and the equipotential lines intersect at 90-degree angles. So that means that, erase that from a previous lecture, if I have, say, a blue flow line going like this, and then say I have a red equipotential line coming down, they have to try to cross at 90 degrees and then do their thing. Now, sometimes it takes your imagination to imagine that 90-degree perpendicular intersection, but that's really what we're shooting for. Okay, next, the area between the flow lines and the equipotential lines must form a square element. In other words, the element length and the element height should be approximately equal. What do I mean by that? Well, again, let's draw a couple of flow lines, say they look like that, and let's draw a couple of equipotential lines. So we want them to try to intersect our flow lines as best as possible. Now, if I had an equipotential line over here, you can see that this element that's formed looks more rectangular than anything, so that's not going to work. We need our elements to be approximately square. Now, again, we're not looking for perfection here, where this distance across and this distance up are about the same. Rule number 3 is that the area between flow lines is what we refer to a flow channel, and the flow rate in each flow channel is the same. So that means then that here the area between these two blue lines that I'm coloring here, this area is what we call a flow channel, and the flow through that flow channel is the same as the flow through this flow channel. So each flow channel we're going to assume has the same amount of flow flowing through it. Rule number 4, the difference in the total head between any adjacent set of equipotential lines is approximately equal, and we're going to call it a head drop. So going back to our example here, the head associated with this point right here and the head associated with that equipotential line right there, those the difference between those is the change in head, and we call that then a head drop. Ideally, we want the head drops to be equal, though it's not totally unheard of, and we'll see an example that we'll do later, that we might have, if necessary, a smaller head drop where maybe this is something that is less than delta H. But believe me, if you keep your head drops between your equipotential lines the same or equal, it will make your calculations a lot easier. Finally, head lines and flow lines must agree with the boundary conditions. And this is kind of a big one. For instance, sometimes we might have, say this is the ground surface, down here is a rock, maybe we have a dam constructed right here, so this is a cross-section through the dam, and maybe we have our water up here and our water down here on the other side of the dam, and so water wants to seep down from here through the soil and come up here on the other side of the dam. Okay, so if that's the case, we have to respect a few things. For instance, if this is impermeable rock, water's not going to flow down through here into the rock, flow through the rock and out, up and back again. That's not going to happen. We have to respect that boundary condition. We also have to respect the boundary condition, for instance, that any point here on this initial ground surface has the same total head. What do I mean by that? Well, imagine again if I put a piezometer down to that point right on the ground surface. How high is the water going to rise up in that piezometer if I just leave it alone? Well, it'll rise up to the top of the water surface. Well, what if I do a piezometer right here and right here? How high will the water rise there? Well, it's just like the first one. It's going to rise up to the same level of head or energy that's in the water surrounding it. My point being that any one of these points on this ground surface here have the same total head. Therefore, by definition, I could connect them with a line, and that would be one equipotential line. So the ground surface, or my boundary condition, is one of my equipotential lines. So I need to respect that. If I have, for instance, one of the mistakes some students will make when they're drawing equipotential lines, whoops, let me redraw my ground surface, is they might say, okay, my equipotential lines are going to look something like this. And what that implies is that this point right here has a different head than this point right here, which has a different head than that point right there. And we know that that's not the case. That's not how it works. Okay. Oh, sorry, that was my cell phone. Now it's silent, and it's not going to do that again. Okay. So now, say we get a flow net. So here's a great example of a flow net in this little picture here, where these dashed lines that I'm drawing in red, those represent equipotential lines. And then the other black lines represent flow lines. Okay, so what can we obtain from a flow net? Well, there are lots of valuable things that engineers might want to use. For instance, Maybe we want to get head distribution or amount of head loss. And so we want to predict or see how much water we can, or how much energy we can remove from the water by forcing it to flow through the soil. Maybe we want to get the flow rate Q through the soil so we can predict how much water is actually moving through the system. We can predict gradient. So gradient is just going to be, if that distance is length L, and that's head 1 and that's head 2 on those equipotential lines, then gradient can simply just be H1 minus H2 divided by the length between those equipotential lines. So gradient could be something very, very useful that we can get from flow nets. We can, if we can get Q, then we can also get discharge velocity V, because we know that velocity and area are related to Q. And we can also get pressure. Pressure being P, it's a very useful term. And we can use that in the design of dams or those kinds of things. Okay, so here's some very practical suggestions that I want to give you for drawing flow nets by hand. We discussed the rules, and now these aren't rules, these are just tips that are going to help you hopefully. The first tip is I recommend that you use some good quality thick paper that can handle a lot of erasing. Don't use flimsy engineering paper or recycled paper. Running your eraser over that a few times and you're going to rip a hole right through it. I recommend when you draw the flow net on your paper for the first time, or actually draw just the problem, before you draw the flow net, draw all of your permanent boundaries, like the ground surface, maybe the impermeable layer beneath the soil. Draw all that in dark black ink. Draw if you have a hydraulic structure like a dam, draw that in ink. And that way, if you erase flow lines or equipotential lines, you don't have to keep redrawing those boundaries. I recommend that you don't use too many flow channels. I have found that 3 to 6 flow channels is adequate. If you're putting more than 6 flow channels on a problem, you're going to be doing a lot of drawing and erasing. 3 or 4 is great. 5 and 6 starts to get a little iffy. I wouldn't ever do more than 6. I recommend that you use a constant number of flow channels, and so don't do any partial flow channels. Instead, if you need to do anything that's partial, go ahead and draw partial equipotential lines or partial head drops as necessary. But for the most part, you really don't need to worry about that too much. I recommend that rather than try to draw the perfect flow net from the start, quickly and lightly sketch your lines initially. Just do a quick and dirty sketch. And don't spend too much time or be too careful with it. Just throw something on the paper and then start modifying it. In general, I found with most students that 3 tries is about what's required to get a good flow net. If you're going back and erasing and re-erasing stuff more than 3 or 4, 5, 6 times, you're probably being a perfectionist, and I don't think that extra perfection is going to give you a better answer when you start using the flow net for calculations. And that leads to of course, my last point. It's easy to become obsessed trying to draw the perfect flow net. Just stop it. Just stop it. Don't worry about that. I generally say, work with the idea that you're going to spend half an hour drawing a flow net at the max. And after half an hour, it's probably going to be good enough to get a reasonable answer. So once we have a flow net, what are some fun things we can do with it? Well, for instance, we can compute the flow through a flow channel. And that's going to be this guy right here, so Q through a channel. And that we can compute that, of course, with the hydraulic conductivity of the soil, and then the total head difference from the first equipotential line to the last. So usually this is from ground surface upstream of your hydraulic structure to the ground surface downstream of your hydraulic structure. That's your total head difference. And then also divided by the number of equipotential line drops, or the number of drops that you had between the first and the last head drops. So that'll give you the flow through any channel. So then all I need to do is multiply to get the total flow, all I need to do is multiply the flow through one channel by the number of channels that I have on my flow net. So my total, or my final equation to compute flow on a flow net per unit width. I mean, that's really important. I should highlight that. This is per unit width into the page. So you got to kind of think of these things in 3 dimensions, right? But that equation that I highlighted right there, that is the equation to get the total flow per unit width of your seepage problem. Now, this equation works if you have square elements, and hopefully you'll draw your flow net to have as square of elements as you possibly can. But what if you don't have square elements? If you have rectangular elements, you got some elements that have a consistent amount of skew to them. All of them are approximately rectangular with the same length to height ratio. If that's the case, then you can put in this multiplier n, which is just the ratio of the height to width of each of the elements in your flow net. So that's how we compute flow in a flow net. So what I want to do now is I actually want to work through an example with you. And some students may come to me and say, boy, it's not fair. Drawing flow nets is kind of hard and tricky. That's kind of mean that you make me draw flow nets. Well, just to show you that I'm a good sport, I'm going to draw a flow net too on this example problem. And we're going to use this flow net to make some calculations. So I've actually set up another little slide here, and we're going to use this slide to draw the flow net. So I'm going to change the color of my pen to blue, and that's going to represent my flow lines. So I'm going to draw the flow lines first. But before I draw the flow lines, I always recommend that you look at your figure here and understand and identify a few things. For instance, let's pull up the black one, black ink. Let's identify our boundary conditions, right? So I know then that this boundary here that I'm trying to kind of highlight, that's my upstream boundary, and I know that that's going to represent one of my equipotential lines. And I know that downstream I have another equipotential line down here. And that's going to be my last equipotential line, because once the water reaches that ground surface, it just runs off and goes away. I also am going to want to demonstrate and establish the habit of right off the bat establish a datum. Okay, so I'm going to call my datum this impervious rock that's down here on the base. That's going to be the datum from which I measure total heads and elevation heads for any point in my flow net. Other things that I might want to point out, this dam is a reinforced concrete dam, so the base of it, where I'm trying to highlight here, is impervious. Okay, so water can't flow through the dam, it has to flow around it. And notice that the dam is keyed into the ground about 5 feet, and that between the bottom of the dam and the impervious rock we have 35 feet of this soil. We're going to assume then that this soil is homogeneous and isotropic. You'll recall from our previous lectures, homogeneous means that whether I have a point here, or a point over here, or a point over here, or a point over here, it's going to have the same hydraulic conductivity. And isotropic means that for any given point, the conductivity in the vertical direction is going to be assumed to be equal to the conductivity in the horizontal direction. Okay, so now that we've got those things out of the way, one thing that I want to also look at here is I'm going to try to study and see if there is symmetry in my problem. Symmetry just means that my flow net should kind of look like a mirror image of itself. And in this particular problem, I definitely see symmetry. I see, for instance, no hydraulic structures like a sheet pile wall, or that might look like something like this sticking down from the bottom of the dam that might prevent my flow net from looking like one another, like a symmetrical image of itself. So if you have a flow net that should have some symmetry, it will make drawing the flow net just a little bit easier. Okay, so going back to my blue pen, I always like to start drawing the flow lines first. So because I have symmetry, I know that my flow lines should start there, and it should come out about the same distance from the entrance. Actually, yeah, about right there. That looks pretty good. So what I'm going to try to do now is draw just a quick sketch of this flow line coming out about right there. Okay, there's my first flow line. Fantastic. Okay, my next flow line, I'm going to say the drop of water enters right there. It should come out about right here or so if I have a symmetric. There. Okay. Flow lines are easy to draw right off the bat because it's kind of easy to imagine what the direction that a drop of water would take to flow beneath a structure. That's a little bit easier to imagine. Okay, so now I'm going to switch my pen to maybe red. That should show up good for the equipotential lines. So now, again, remember, I'm looking for nice square elements. So I got to start here, maybe on the corner, and whoops, I want to end the show. And I'm going to come down, and I'm going to try to cross these flow lines at as close to 90 degrees as I can get. Now, I know you have to definitely use your imagination. But I'm trying to keep the elements somewhat square, like the distance versus the height. Obviously that one's going to be lacking. We'll need some work. Maybe right there. Okay, maybe right there. I'm going to come over here now to the other side and start over here with the idea that, I'd like to get a little bit of symmetry. Well, I don't like that line. I'm going to come down and try to get it maybe just a little more square. Nope, I went too far. Let's come down. Maybe like that. Cool. Maybe like that. Maybe like this. Okay, now this is where we get to the idea of partial head drops. Because you see I have this nice big rectangular element. If I come in here and draw one more element to try to make, maybe that a square element, this section right here is obviously not going to be square, and that's okay. You can live with partial head drops where you have one set of head drops that doesn't make rectangular elements. We can live with that. Okay, so I would go back and I would start erasing and some of these equipotential lines. I would maybe identify some places where it might need some work. So for instance, this element right here doesn't look very square, So I'd probably go back and work on that a little bit. Um, so a lot of students go, whoa, Dr. Frankie, what about these corner elements here where I'm circling? Those don't look square at all. Those are freaky looking. Yeah, they are. But we don't really worry about stuff that's in the corners, where I'm kind of highlighting here, because the flow is not really going to be very big in those corners. Flow is the greatest on a flow net where you have the smallest elements in your flow net. Where you have the smallest elements, that's where the water is flowing the fastest. And so just like it, if you think about it and just try to use common sense, where is the flow going to be greatest around this dam? Well, probably right beneath it, right? And the further away you move from the dam down here, the flow is probably not going to be, or I should say the velocity is not going to be as great because we have a bigger area through which the flow is occurring. The flow is going to be the same through all of these flow channels. What's different is the cross-sectional area. And because the cross-sectional area is different, the velocity of the flow is different too. So let's count how many equipotential lines I have between my first, so this is my first line, the ground surface, and this one here is my last. So I highlighted those in black just so I know. So how many equipotential lines to get from, say, if I have this dot and I want to move it all the way to the last equipotential line. So 1, 2, 3, 4, 5, 6, 7. Actually, let me start over again. 1, 2, 3, 4, 5. Now, this one isn't like a full jump, so I would call that maybe a 80% of a jump, maybe. So 0.8. So 1, 2, 3, 4, 5. 5.8 to get there. 6.8, 7.8, 8.8, 9.8, something like that. Okay. So I got 9.8 jumps or drops. Now, if I go back and revise this, I might change that and get a different set of drops, or, but that's okay, for this initial example here. Now let's go and look at the solved problem on our lecture. So this picture here represents the actual completed, like a perfect solution. And isn't it interesting that the perfect solution also had a partial head drop of 0.8 kind of there in the dam. So all that means is we couldn't get one more full drop in there and still keep square elements everywhere else. So here's a couple of things. Again, there's my datum like I had before. What was the head then from my datum up to the top of that water? Well, it was 60 feet. You recall that the elevation of the soil from the datum to the ground surface was 40 feet. And then we've got another 20 feet of water upstream of the dam. So that means that from my datum, the total head is, for any one of these points upstream from my dam is going to be 60 feet, meaning if I put a piezometer down to any one of those points, the water will rise up to this elevation right there, which is 60 feet above my datum. Okay? Then downstream of my dam, the water rises up just to barely the ground surface right there, which means that should be 40 feet above my datum. So what is my total head loss from my first equipotential line to my last equipotential line? Well, it's simply the difference in the total head upstream and downstream. So 60 minus 40, it's 20 feet. All right, how many drops do I have? Well, I have moving from the starting point there all the way to get to the last equipotential line. Okay, so I have to go 1 drop, 2 drops, 3 drops, 4 drops, 5 drops, 5.8 drops, 6.8, 7.8, 8.8, 9.8, 10.8, 11.8 drops. We have 11.8 head drops. Now in my quick and dirty sketch that I did in less than 5 minutes, I came up with 9.8 head drops. But interestingly enough, how many flow channels do these guys have? They have 1 channel, 2 channels, 3 channels. They have 4 flow channels. I had 3 flow channels. So it's not like my solution was wrong. It's just that the fewer the flow channels you have on your problem, the fewer the equipotential lines you're going to have, because your elements are going to be larger squares. So my guess is that our answers would be about the same. And then the number of flow lines on this, again, is 4 channels versus on the quick and dirty one that I drew before, that was 3 channels. So if I wanted to compute the flow for this problem, all I have to do is plug and chug. So remember, hydraulic conductivity is given to us. It's 1 foot per year. The head drop, the total head loss from first to last equipotential lines is 20 feet. The number of drops here is 11.8 drops, and the number of flow channels is 4. And that's going to give us 6.78 cubic feet per year. Nice. So with my quick and dirty flow net, how would I do? Let's go ahead and compute that. So that would be 1 foot per year for K. The change in head, that would be the same. That would be 20 feet. That doesn't change. But the number of drops changes. So I had 9.8 drops. Oh dear. I'm right at the bottom of the screen. You can't see that. But I'm going to put 9.8 in. Come back. I'm going to put 9.8 in on the denominator there instead of 11.8. And I had 3 channels. So I'm going to pull out my trusty HP 48GX calculator. It's getting hard to find these anymore. Okay, punching in my numbers, I get 6.12 cubic feet per year per foot. So look at that, guys. I mean, this picture shown here that you're looking at right now is drawn very, very precisely. And in 5 minutes, I put together a solution that was, just maybe 1/10 of a cubic foot. I'm sorry, that's too much. Maybe what, 7/10 or 6/10 of a cubic foot per year per foot off, which is pretty close. And with a little bit of refinement, we would have gotten that answer even closer. So the whole point of doing this extra little calculation is I just want you to see that even with a quick and dirty flow net, we can get some pretty good answers. Okay, so let's go ahead now and show you how we might use the flow net. Say we want to determine the pore pressure at point B under the dam. So if I go back, point B is highlighted right here. So it's sitting right on this equipotential line that I'm highlighting, right beneath the dam. Okay, how do we get pore pressure? Well, we're going to use our Bernoulli's equation. Always use Bernoulli's equation with flow nets. That's your governing equation. What do I want to solve? I want to solve for pore pressure. Pore pressure is just this guy right here. So all I need to do is rearrange that equation to solve for pore pressure. Okay? So remember, this Z, that's our elevation head relative to the datum, and H sub B is the total head. Well, where in the world do we get total head? Well, we get those from the equipotential lines. Think of the equipotential lines as energy contour lines. And if we have labels on our energy contour lines, then all we need to do is interpolate where our point is relative to the closest equipotential lines, just like you're reading a contour map, like an elevation contour map. Or we can go ahead and just compute it. So the head at B is going to be our boundary head. Our boundary head is, remember, just our initial boundary right here upstream of the dam. And that's going to be minus the head loss per drop times the number of drops from the boundary to point B. So, basically what we're going to do, folks, is we're going to say, okay, I know the head at that line right there. What I want is the head at B right there. Okay, so if I know the head at my first equipotential line, I want to know what's the head on this line, the head on this line, the head on this line, until I get down to point B. So all I'm doing is just subtracting head until I get to my point of interest. So let's compute then the amount of head loss per equipotential drop. And I'm going to call that little delta H. So it's going to equal my total head loss divided by the number of drops needed to get that total head loss. So I had 20 feet of total head loss from upstream to downstream, and you'll recall that I had 11.8 equipotential drops in my flow net. So that ratio gives me 1.69 feet of head loss for every drop that I go for each equipotential line. So that's the head loss per drop. Now, the number of drops from my initial boundary condition to where point B is 4 drops. I mean, so if I go back here, here we go, from my boundary condition upstream, there's 1 drop, there's 2 drops, there's 3 drops, and B sits right on the 4th drop from my initial boundary condition. That's, I guess, drop 0. Okay, so that's why I have 4 drops right there, and times 1.69 feet per drop. So I get 53.24 feet of total head at point B. Again, where do I get total head? I get total head from the equipotential lines. It's just like reading a contour map. Okay, so now I just plug this guy into this equation for total head. And where do I get elevation head? Well, I get elevation head by measuring the vertical distance from my datum up to point B, and that's equal to 35 feet. So I just plug it in, and I get 1,138 pounds per square foot for my pore pressure at point B. So what can we do with this? Well, let's show you another example. Example number 3. Point B is sitting right here beneath our dam. And we already computed its pressure to be 1,138 pounds per square foot of pore pressure at that point. But what if we compute the pressure at that point, and at that point, and at that point, and at that point? We compute the pore pressure at all of these points. If you think about what pore pressure is literally just pressure that's trying to push stuff off of it. If I have this big dam sitting on that pressure is going to try to uplift this dam. If it tries to uplift it, then the water behind the dam might actually push the dam downstream and cause a massive failure. So if that's the case, then that would be a huge engineering disaster, and we want to avoid that. So what we're going to do then is we are going to compute the uplift force on the base of the dam. And remember that force simply equals the integral of the pressure. So if I have pressure if I compute or redo what we did in example number 2 for all these different points along the base of the dam, I can compute, a pressure at, this point number 1. Actually, to be consistent, why don't I just call this point A, that's point B, point C, point D, point E. If I compute the pressure at point A to be 1402 psf, we already did the pressure at B, pressure at C, 927 psf, pore pressure at D is 716 psf, and pore pressure at E at 453 psf. I can use a basic integration technique like, I don't know, Simpson's rule, or the trapezoidal rule, to approximate the integration of the pressure on the bottom of this dam. So here, in these calculations down below the figure is exactly what I did. All I'm doing is I'm taking the average pressure for each one of these blocks of pressure down here on the bottom of my dam. And all I'm doing is I'm summing the area of them. I know each one is 15 feet long or in width, and I can get the average pressure in terms of the height of these rectangles. And so I'm just plugging those in, and I'm getting summing those up, and as I sum that area, I get this value right here. So remember, this is a force per unit width of length into the dam. So that's accounting for the third dimension into the screen. Cool. And what else can we do? Well, we can determine the maximum exit gradient downstream of the dam. The location where you have the maximum gradient on a flow net is the location where you are most likely to get erosion and soil carried away by the seeping water. So where does that occur? It always occurs where the element has the shortest length between head drops. And that's always the smallest element. So if I go back and look at the flow net, I'm looking at the toe of my dam, and I have this little teeny element right here. That's going to be the place where my seepage is, where my velocity, I should say, of my seeping water is the greatest. And so if I physically measure, take out my ruler and I measure the length from head drop 1 to head drop 2. Let me draw it in blue. If I measure this length right here with my ruler, it comes out to be about 4 feet. So we know then that gradient is simply the change in head divided by the change in length. And going from head 1 to head 2, we know is simply the same as the total number of drops divided by the the total head loss divided by the total number of drops on my flow net, which was just that 1.69 feet per drop we computed earlier, divided by 4 feet, and that's going to give me my 0.42 as my maximum exit gradient. Now, how is this meaningful to us? Well, we've learned through research that if the exit gradient is around 1 or greater than 1, it's usually indicative that the water is going to be carrying the soil particles away and causing erosion beneath the dam, which could be very, very bad. Last thing I want to talk about with flow nets is what do we do if we have anisotropic soil? Now, you remember from our example, we assumed that the soil was isotropic. The soil in the field is never isotropic. It's always anisotropic, which means that the conductivity in the y direction is not equal to the conductivity in the x direction. And in fact, what we see is that the conductivity in the y direction is always greater. I'm sorry, I didn't mean greater. It's always less than. It's less than the conductivity in the horizontal direction. Water has an easier time flowing horizontally through soil than it does vertically. So if we can estimate or know these actual vertical and horizontal conductivities, then all we need to do is transform our flow net or our boundaries, our units on our drawing, to an equivalent isotropic setting. So in other words, I'm going to take this x-axis and I'm going to transform it to a new x-axis, this x bar. So if you look at it, it kind of looks like you took your fingers to the cross-section on the left and you just squished it all together to get this cross-section on the right. And we do that using this transform equation right here, where we compute our new x-coordinates with the old x-coordinate times the square root of the ratio of the vertical to the horizontal hydraulic conductivities. So for example, let's say that we have a vertical conductivity of 1 foot per year and a horizontal conductivity of 9 feet per year. If I use this equation to the left, the square root of 1 divided by 9 is simply equal to 1/3. So that means then that the new x-coordinate is just going to be 1/3 of, or 0.33 of whatever the old x-coordinates were. So I'm just going to shrink in my x-coordinates by 1/3. So then once you draw your geometry with your transform section with your new x-bar coordinates, the next thing we're going to do is compute an equivalent permeability. So an equivalent isotropic permeability, that's this guy right here. And we're going to use this geometric mean equation. And once we have our equivalent hydraulic conductivity, then we're going to draw the flow net just like we would like normal, with nice square elements and with all the rules we talked about, but we're going to draw it using these x-bar coordinates. And then once we have the flow net drawn, we can compute seepage using this equation right here. The only difference is we're using the equivalent K and our flow net drawn on the transformed axis rather than the original linear axis. All right, folks, well, that does it for flow nets. I know this is a lot of material to digest, but I encourage you to get a head start on your homework. Don't delay or procrastinate this flow net homework because it can take some time. And the more you get practicing with it, the sooner I think that you're going to pick it up. So with that, that's the end of this lecture, and appreciate your attention. I'll catch you guys in the next lecture.